be studying the design criteria, how to do the checking, like just like in the case of the block type foundations. Here also we have principal design requirements, so we'll see those, and they are slightly different from the block type foundations. The two criteria are, one is the frequency criteria and the other is the displacement amplitude criteria. So we'll just have a look at both. So in the case of the block type foundations, we have we know that the frequency ratio should be either less than 0.4 or greater than 1.5. So the criteria here is that the natural frequency of the system should be at least 20% away from the frequency of the machine. So it's expressed in a different way, and preferably it should be 50% away. So here everything is expressed in terms of the frequency of the machine. So we can express that it should be either 0.8 times the frequency of machine, or it should be greater than 1.2 times the frequency of the machine. So if we now want to express it in terms of the frequency ratio the way we have done in the case of the block type foundations, we can do that also. So in this particular case, we say that the frequency ratio R should be greater than 1.25, or R should be less than 0.833. Okay, so these are the criteria here. So this is the minimum requirements, and the desirable point of view also we can just express that the natural frequency should be 50% away. So from the preferable considerations we can write like this. That your natural frequency should be less than 0.5 times the operating frequency of the machine, or greater than 1.5 times. And if we want to put it in terms of R, we say that R should be either greater than 2 or R should be less than 0.67. And the next criteria is the amplitude. Now in the case of block type foundations, we were following a curve. Now here we have stricter requirements in the case of the frame type foundations, and the requirements, they depend on whether the RPM is less than 3000, which is 50 Hertz, or it is greater than 3000 RPM, that is greater than 50 Hertz. So basically why 50 Hertz comes into picture, because the high frequency machines, they are classified as those above 50 Hertz. So we have these machines which are less than 25 Hertz, they are low frequency machines, and the ones which are in between 25 and 50, they are medium frequency machines, and the ones which are greater than 50 Hertz, they are high frequency machines. So accordingly the requirements are different. So continuing further, so now next we need to now specify what are the limitations on the horizontal and the vertical amplitudes. So here we see these in a different way, independent of each other. So for the machines which are less than 50 Hertz, the vertical amplitude is limit is 40 microns and the horizontal one is 70 microns, and this is reduced for the machines which are high frequency machines. So it's 20 microns and 40 microns respectively, the vertical and horizontal. So it's also specified that we need not combine the vertical and the horizontal amplitudes because they occur independent of each other. So we need not do any combination of the horizontal and the vertical amplitudes. Now the next is the net bearing pressure below the soil. So under the worst combination, the net pressure below the footing, it should be less than 80% of the allowable net bearing pressure specified in the geotechnical report. Alright, so these three are the principal design criteria are to be followed for the case of the frame type foundations. Okay, now let's see other important aspects on the analysis. So now we go into the methods of analysis. So first of all, we have to do static analysis here, and we also need to do secondly the dynamic analysis. So both types of analysis are required here in the case of the frame type foundations. Now this is the I'm just showing you a screenshot from the code IS 2974 part 3. So basically it recommends that for static analysis has to be done for these loads: dead loads or operating loads, then the normal machine unbalanced loads. So this is also specified by the manufacturer. Then the temperature loads. So we have to consider uniform temperature change and also the temperature gradients. Then short circuit forces are specified by the manufacturer. Then loss of blade unbalanced force or bearing failure, this is also provided by the manufacturer. Then seismic loads we have to calculate ourselves. So essentially we have to do these loads, the analysis. So this is done basically static analysis. And then the load combinations are also specified here. Here the load combinations are the operating conditions, dead loads plus operating loads, plus normal machine unbalanced load, plus thermal effects. Then we have the short circuit condition. So short circuit condition is dead load, operating load, normal unbalanced load, thermal loads. And besides this, we have the short circuit forces are also to be considered. Similarly, for the case of the loss of blade condition or bearing failure condition, we replace the short circuit forces by the forces for the loss of the blade. So that is accidental. Alright, and then finally for the case of the seismic condition also we need to check. So these are the various load combinations we need to check the foundation. So for this we run the static analysis.
Just one thing, sir. What is the short circuit condition?
Short circuit condition. So is a electrical failure, and the forces associated with this electrical shock, they are to be specified by the manufacturer. It's an accidental case. So we have the load cases. I'm just highlighting again. So these are the those load cases we have to consider, and we have to do static analysis. So it's the code says that a detailed static analysis of the foundations shall be performed to ensure that the foundation carries all the loads safely. So the same model which has been used for dynamic analysis may be used for static analysis. Now it talks about the dynamic analysis. So when do we and why do we need the dynamic analysis? Anyone can guess? So the answer is that static analysis is fine for the load combinations, but then dynamic analysis is necessary for frequency check and for the amplitude check, because the amplitude check has to be done for the dynamic condition, operating condition, and also the we need to determine the natural frequency of the foundation. So for that only we do the dynamic analysis. So basically, whether we are talking about the static analysis or dynamic analysis, there are two ways. Either we can do it manually. For example, frames, regular building frames, we can analyze them manually, which is a bit tedious process. Say moment distribution you are using or approximate method you are using. And similarly for the case of the dynamic analysis, there are approximate methods available, which is basically the principle behind is to idealize as a single or double degree of freedom. Now because we have the matrix approach, stiffness approach, and the FEM, so we don't follow, but just for the sake of knowledge, we are just covering that earlier these manual methods of analysis were used for dynamic analysis also. The one method was the resonance method, that was a single degree of freedom idealization. Then there was this amplitude method, which was 2 degree of freedom idealization, or the double degree of freedom idealization. And then we have the combined method also. So combined method is also basically double degree of freedom idealization, but then it combines the resonance method and the amplitude method, because the resonance method is based on mainly the frequency check and the amplitude method is based on the amplitude calculation. So this combined method basically combines both. So the manual methods, they are quite tedious and less accurate, so they are very time consuming also. So nowadays we prefer the numerical approach. You have already learned the stiffness approach in our advanced structural analysis, and you have also done the finite element method. So we can either do space frame modeling, and the space frame modeling we can do 2D or 3D, but we prefer 3D analysis is better. Code also recommends that we should do 3D analysis. Or we can do the finite element modeling with solid 3D elements. So these two approaches are possible. So in the case of the frame analysis, space frame analysis, you already know the basics. So MATLAB program also, you have your own program, and in fact you can use your own program also for this purpose. So here we idealize in as a space frame, and what we do at the bottom, where the connection of the frame is happening with the sole plate, we do fixity. So point of fixity are basically the point where the columns, they are meeting the slab, the base slab. And the top deck, if there are no cutouts, then we should consider the slab effect also, the diaphragm action. So diaphragm action, we can model them, either we can take them in the formulations itself, just like we have learned in our advanced structural analysis course, or if we are using STAD, then you can make use of the horizontal braces. You can apply braces with pin conditions at the ends, and this also takes care of the effect of the slab. Or you can properly introduce plate elements also. Both options are there. So now as far as the solid 3D FEM is concerned, we'll just see how it looks like, the model. So basically there are softwares available, ANSYS and Abacus. They are very common software which are very well versed for this purpose. So here we are showing the model based on the space frame. So these are the space frame based models. So in one case we are using braces, other case we are using plate elements. But remember, the braces, they have been applied on one panel only. The other panel which had cutouts, braces are not applied. And this is the complete 3D FEM model using the brick elements. So both these are taken from reference MTech thesis. The modeling part, so I'm just holding it so that we can read. So it the code says that the analysis shall be done using simulated mathematical model of linear elastic properties for turbo generators of more than 100 megawatt capacity. A 3D space frame analysis is recommended. So we should not go for 2D analysis. If we have 100 megawatt or more, then we should go for 3D. So the modeling should take into account the basic characteristics of the system, that is mass, stiffness and damping. Special attention is required while idling the points of excitation. The model should simulate the vibration characteristics of the machine foundation system to a sufficient degree of accuracy. So this is what is preferable for the case of the analysis. Okay, so let's just go further. The code says that foundation shall be modeled as a three-dimensional space frame in which columns and beams are idealized as 3D beam elements with 6 degrees of freedom at each node. So this you can do very well. 3D frame model you have already learnt in your structural analysis, advanced structural analysis. Slabs and walls, if present, may be modeled using thin shell plate bending elements. The columns shall be assumed to be fixed at the base, disregarding the base mat. Alright. So then nodes shall be specified to all bearing points, beam column junctions, midpoints and quarter points of the beams and columns, and wherever the member cross sections they change significantly. So it says that we should specify nodes where there are bearing points. So even if we have one single beam, but if there is the loading point, so we should discontinue. In the modeling case, we should discontinue and have nodes at those locations. But now the STAD, it allows us to apply load in between also, so there is no issue. We can apply as a member load. So either we consider node at that point and we apply the loads as joint loads, or we consider the member as continuous and we don't give it a break, and then we apply the loads at the as a member load. So both options are possible. Okay, now we consider the dynamic analysis. How do we consider the dynamic analysis? And then we'll also study about the soil structure interaction. So dynamic analysis, we have to do two analysis: free vibration analysis and the forced vibration analysis. So I hope you know what is free vibration analysis. So free vibration analysis basically is eigenvalue problem is to be solved, and what we need the natural frequencies and the mode shapes to be determined. So here we just ignore the damping and our model is like this. So essentially we need the mass matrix and the stiffness matrix. Damping matrix we are ignoring anyway. So this eigenvalue problem you can very easily solve using the program you had developed in your advanced structural analysis also. So this is the free vibration analysis, means there is no force, so damping is ignored. So all we need is mass matrix in addition to the stiffness matrix. So we need to lump the masses at various nodes, and then we solve the eigenvalue problem. We get the solution in terms of the natural frequencies and the mode shapes, because we have to do the frequency check. So that's why we do this analysis. All right. So as the output we get the natural frequencies and the mode shapes. So if you have your own program for the analysis stiffness approach, all you have to do is include the mass matrix effect. That's all, because the natural frequencies will make use in the frequency check. At least how many natural frequencies we must obtain? We know the operating range of the machine. So in the operating range we should at least get all the frequencies and all the modes, and a little bit beyond the operating frequency also, because the machine is switched on. So when the machine is switched on and it's progressing, so it will it will pass through the frequencies from 0. So code says that free vibration analysis shall be carried out to calculate the natural frequencies and mode shapes of the foundation. The highest natural frequency calculated should be at least 10% higher than the operating frequency of the machine. Damping may be neglected for the purpose of vibrational analysis. Okay. So that's what the code says. And then the other analysis is the forced vibration analysis. So if you just see the bottom, yeah, forced vibration analysis. Why do we do forced vibration analysis? So forced vibration analysis is done to obtain the amplitude. So the forced vibration analysis basically is done to obtain the response. So basically if we have the forcing function, so forcing function is sinusoidal, and then what happens is that we need to find out the response. So response will always lag behind the force. Why? Because there is a damping, so the response lags behind the force, so we have to find the phase lag. But here what is more of interest is the amplitude of the vibration, the displacement amplitude, because that we subject to the checks. The displacement amplitudes, horizontal and vertical, we need to calculate. Now, how this harmonic or the forced vibration analysis is done. So basically, we can make use of the STAT or ANSYS, but let's just also see theoretically what or how it is done. And in fact, for harmonic analysis also, you can suitably modify your stiffness approach program which you made as part of our course CVL 756. So here basically we don't ignore the damping also, we consider damping also, but then we take advantage here of the harmonic nature of the vibrations. So because the vibrations are harmonic and we should have the forcing function also with us, the manufacturer provides us the information. So everything is operating at the operating frequency of the machine. So omega m is the operating frequency of the machine. So now, taking advantage of the harmonic condition, the velocity and acceleration, they can be expressed in terms of displacement now. So velocity is j omega times the displacement, and similarly the acceleration is also minus omega square the displacement. And then once you substitute this, we get a very closed form solution, and we can get a solution. So in fact, we get a solution something like the static analysis, because here the dynamic components, they will cancel out on the both sides. E to the power j omega t, they will get cancelled out, and we'll get a very good closed form solution just like the static analysis. Only thing will be that there will be now the additional terms. It will not be just the K or the stiffness matrix. There will be terms like the mass matrix and the damping matrix. So e to the power j omega t, so the dynamic component basically gets cancelled out, and we get a very closed form solution. So here also, if you want, you can modify your program of the stiffness method, and you can get a closed form solution. So what we need is the operating frequency omega m, the mass matrix, and the damping matrix also. So that's how the software, they do the computations. We have ANSYS can do this, STAT can also do this, but of course STAT can do best for the case of the space frame. And then for the accidental case, for example, the case of the short circuit condition or the blade failure, we have transient dynamic analysis. So what is transient dynamic analysis? This also you have already studied in your dynamics course. So here the forcing function is a bit different. So either we have impact kind of forcing function, or we have irregular non-periodic forces. So we can have an impact kind of force, or we can have a forcing function irregular like the case of the earthquake. So for this, we need to do the time history analysis, and that can be done. However, the code recommends that these time history analysis can be avoided, and we can do equivalent static analysis, because we have already taken into account the fatigue factor. So equivalent static analysis is usually done. We don't do the dynamic analysis for this kind of forcing function. So we do dynamic analysis only for the case of the frequency, natural frequency determination, and for the case of the amplitude determination. Okay, so continuing further, now we'll just see about the case of the soil structure interaction. Yeah, so in certain conditions, code recommends soil structure interaction also. So if we have to do soil structure interaction, then we have to model the base slab also. For example, here base slab has been modeled. You see here base slab is modeled, and its base slab is further connected to the ground by means of springs. So springs are introduced. So this is a bit complicated, and in some exceptional cases this is also required. Yeah, so the code says that effects of soil structure interaction on the dynamic response of TG foundation may be ignored under steady state dynamic loading. So steady state dynamic loading means when the machine is operating and we have steady state conditions, harmonic loading. However, if the TG foundation is located in zones of high seismicity, soil structure interactions shall be considered for seismic analysis. So high seismic zones like zone 5 or where we have these kind of situations, then we need to do the soil structure interaction also, modeling the soil as springs. So no soil structure interaction need to be considered for static analysis. It is sufficient to model the foundation fixed at the base raft level. So in general, we just model the frame to be fixed, the columns to be fixed at the top of the base slab. So that's enough. So the soil parameters, the stiffness of the soil in that case does not enter into picture, because we have chosen a very stiff, very thick base raft. So the soil becomes less important. All right, and here I'll also show you the model, like the code shows an example that this is one foundation and this is being modeled using the space frame analysis like this. Now you see the space frame model. I'm just fitting it. So this is the space frame model. So here nodes have been created at all the locations where there are either loading points or where there is any change in the shape or something like this. So a lot of small elements they have been created. So this is how the modeling using space frame analysis is suggested. So fatigue factor, it says that a fatigue factor of 2 shall be used for the dynamic forces caused by the normal unbalance. So when we are doing this static analysis and the load combinations, so we must use a fatigue factor of 2. So fatigue factor of 2 is used when we are doing the stress calculation, but fatigue factor need not be used when we are obtaining the displacements. When we are obtaining the natural frequency, when we are doing the free vibration analysis, that time no force is applied, zero force. So this does not come of any relevance at that time. And when we are doing the harmonic analysis, that time also the fatigue factor is not to be applied. Alright, so this is very small code, so you can just have a look. You can just scan through the various provisions of this code. It will be good. And next thing is that I will also share with you a report, an MTech thesis in fact. So I'm just opening that and I'll just show you this MTech thesis. Is very interesting, and you all read that MTech thesis. Yeah, so this is the thesis of we had completed in 2012, Shagufta, and she is a senior engineer and an expert in designing different types of machine foundations. She has a lot of practical experience, and this project was done as a part of the MTech thesis, and you can just go through this. So I'll just highlight you some of the important points covered. Literature review is very exhaustive. It talks about even the manual methods, and then we just take you through the main chapters. Yeah, so this is the foundation. This was a practical foundation which came to her for design. So this was taken up by her, and this is the modeling. So she did modeling both the space frame as well as 3D finite element method, and she also considered the soil structure interaction. So the pictures I presented during my presentation, they are from here. So now you see the modes of vibration. So different modes of vibration, they are found using both STAD as well as using ANSYS. So the upper one, this is the STAD model, and the bottom one is the ANSYS model. So various modes. So complete modal analysis was done by her, and then after that the harmonic analysis was also done to get the amplitude. So harmonic analysis, in fact, she has done over entire range of frequencies. Now you see this is the harmonic analysis. It's like a sweep harmonic analysis at various frequencies is done, and then the complete plot is there. So, and then the soil structure interaction also is covered here. So I think you can all read this thesis. You will find it very interesting. So this is her model with soil structure interaction in ANSYS. So this thesis I'll send you. Alright, so now I think I will just stop here, and if you have any questions, you can ask questions. So basically, we will from next week we'll start some practice also in the case of these frame type foundations, because the best way to learn is by practicing. And I hope every one of you have got my email on how to install STAAD, and some of you may have installed STAAD also in your computers. So you have any doubt, please raise your hand on what we have covered. The theory part is less in the case of the frame type foundations. Yes, any doubt? Any yes, Supriya.
Sir, why we are not considering damping in free vibration analysis for calculation of natural frequency?
Free vibration analysis is like that only. We don't consider the damping. It's undamped free vibration analysis. Okay, the mode shapes etc. They are for undamped condition. We ignore damping.
Okay.
Okay, but we know that the damped frequency is will be slightly higher than the undamped frequency. Okay, so even if you include damping, it will not change the results too much. So it's better that we ignore damping and do undamped free vibration analysis. Then we get the natural frequencies and the mode shapes.
Okay, sir. And right. Sir, another question is, if we do a solid modeling, then what are the necessary checks we need to perform? I mean, in case of frame model, we can check the moments and shear. In plate, we check the stresses.
See, this like is a good question. Y direction. See, if you are doing space frame analysis, output will give you all the moments. It will give you all the shear force, bending moments, axial forces. Now, but if you are using solid modeling, you will not get these directly. Bending moments, shear forces, you will not get directly. So in that case, you have to calculate them indirectly from the strains. You have to get, for example, the strains at on the two extreme fibers, and from the values of the strains, you have to calculate the axial force and the bending moment. Okay, you will not get them directly. So that's issue. Okay. And here another point is that in the case of these frame type machine foundations, we have to use the working stress approach. How many of you are familiar with the working stress method of analysis and design? Are you familiar with working stress method of design? Has anyone done or learned the working stress method of design? Working stress method of design is in fact simpler as compared to the limit state approach. Only thing is that nowadays it's not taught, but if you open IS 456, there is a section on the working stress approach. So machine foundations are to be designed by the working stress approach. Okay. Any other question?
Another question. So another question from previous class is, you have said that the cantilever should not be higher, it should be within 500 mm or something. So is it a case that we need to make the structure in such a way that it will be a corbel type of thing?
It will be?
Corbel.
No, not necessarily. See, these overhangs etc., they will be specified by the manufacturer of the machine.
Okay.
So if the manufacturer of the machine needs them for some purpose, then you have to provide them.
Okay, sir.
But if, for example, you find that the design is coming very uneconomical because you have done the analysis and you are finding that the inertial forces are very high, then you can talk with the manufacturer and you can of course tell him that this is the case, that overhang the force is coming very high and then it will be uneconomical to design it. You can always talk with him. So in general, it's from the just our one's experience that if we are keeping small these cantilevers, then the forces will not be very high. But if large cantilevers, naturally the forces will be very high. 1 meter and above, forces will be very high. You have done these calculations also in your assignment. Okay.
Yes.
Any other question?
No more questions. Thank you. Sir.
Anyone has any question? So if no question, then I think we can have the attendance. I'm just opening the attendance sheet. Dr. Dhawan, you want to talk about the foundation? Dr. Dhawan, you want to talk? Because you wanted 10 minutes.
Yes, yes. Give me 10 minutes, if possible.
Yes.
I'll talk something general.
Yes, we have sufficient time.
Understanding the concept of structure. So,
please continue.
Please, I'll just talk general because we have been listening this semester for vibration machine foundations. I'll just talk general thing which you will be actually applying in your when you take up the assignment. We are discuss here in MTech the dynamic analysis, advanced structures, machine foundations, structural and more. But I would like to say that any structure that we deal, first of all, we need to know the structural system, and then initially we need to make a design basis report. Design basis report means the architecture drawings we have to clearly understand what is the structural system, what are the loads that are going to be put on the structures, whether it is dead load, high load, wind load, or any other type of loads. The first thing that will start after knowing the geotechnical investigation report, we will make a design basis report of explaining the total structure system that this building is frame structure, shear, whatever is there, and these are the type of loading, and this is what we are going to do. Analysis part, the dead load, live load analysis, wind analysis, earthquake analysis, and the combination of loads. The entire thing we will fix before we actually start, and that will become a very important part. And this will be well documented also. And I think later on after completion, we don't know where are the drawings, who has analyzed it, who has designed. So this becomes a very elemental thing, but very important thing that we need to know. We are going to analyze what are the things, what are the types. So design basis report based on the geotechnical report, we need to formulate and document it properly so that even after the building is complete and then further any investigation on the so that handy for further investigating the existing structure. Now, I will just talk the basic thing that understanding the concept of structural analysis and design, that normally the structure, when we talk of statics, though the external loads, and then we work out the shear force, moment, deflections, and because of the invention of steel and RCC, we are now going for multi-story buildings and large span structures, whether the buildings and bridges. And here we know that now the tall buildings like Burj Khalifa, which is 28 meters high in Dubai, 1 kilometer high building in Jeddah is under construction, and 1 mile high building in Dubai is at the planning stage. Likewise, bridges also, now we are going for large span bridges, the stakeholder bridges, where the span may be more than 1 kilometer. So the basic things that whether we may take help of numerical methods, the application of softwares, but my own experience is that we must know the actual behavior of any structure that we will be dealing, and then we must have to cross-check manually, because if any error with respect to unit, then the results can be erroneous, and then what can happen at the field. So we have to see the structure in totality and verify it by manual calculations, because I tell you my own experience and during my MTech project, I analyzed the 20-story building to 3 degrees of freedom, where there was application of frames as well as shear walls. So I solved it manually and then checked out the result with the computer findings. We have to see that the results that we are getting should be within the range of 5 to 10%. So the manual, because the software is also made by a human being, it should be there. And then finally, as a young engineer, I would say that any job that you do in any office, the documentation part is very important. Now here in IIT, so many buildings have come up where probably we don't know, where is the sector designs, who did the sector designs, what is the basis of that design basis report and further. There is absolutely no documentation. Now, as a young engineer, my message to you is that structure design, because you are doing masters in structures and you will be going to that profession. The documentation part, right, the design report. You must see that now make use of the computer for further documentation in the cloud form or in any form. So that any structure that you need for further investigation, that can be very, very handy. Now, the basic thing which I would like to share further, that the equilibrium and the section force. We are thinking about the RCC grading. The load is columns and then columns to foundation, and then finally it goes to the side. Then likewise, section force here, we need to know the actual force, shear force, bending, moment, torsion, and the application of external force. Now the section force here, the cross gives us actually the resistance and the capacity, and the shear sectional force gives us the strength. And then here, see if we apply moment, then it can hugging or sagging. But bending moment diagram is a different thing. Like that, axial forces may be compression and tension. The shear force becomes a diagram becomes a different thing. Twisting becomes a different thing. But my idea of telling that basics we need to know, and that will be an important tool for us to understanding the structures better. We can further work and get finally talk about anything that you make a habit of keeping your things intact so that you can refer it at your later date. So this is what I want to give you sharing my own experience in the field. Any question you want to ask, you are welcome.
क्या हुआ बेटा मेरी क्लास कर रही है तुम
So everybody is silent. You are free to ask.
Thank you very much, Dr. Dhawan. Dr. Dhawan, thank you very much. And
okay,
students, if you have any question, you can ask. And then this is very interesting part of the course. So from Tuesday we'll be doing the practice part, and today's lecture will be soon uploaded, and you can just watch it again. And today who is absent? Dharam Singh, are you there? Dharam Singh, Namrata Pandey, are you there? Sahil Garg, I think today Namta Pandey, Sahil Garg, and Dharam Singh, they are absent. So I think thank you very much. So you must be now waiting for the next class. Okay, see you then.